Okay, welcome back to class, everyone. It is Halloween, October 31st. So hopefully you guys are having a nice Halloween so far. We're all done with exam 3, so that was over chapter 4. So we're going to begin our second to last chapter of the semester today. And then, so it's the end of week 11, so we're down to the last month or so here. So chapter 5 is about categorical data. So we're going to go back to categorical, but now we're going to be comparing across two different populations. And it turns out that this type of data is very useful for understanding relationships between variables. So if you're going to do some kind of scientific experiment and you're testing to see how one variable affects another, well, it's very likely you would use the techniques that we talk about in this chapter. So so that's what we're doing here in chapter 5. Let's see. So we do have one more midterm. So that'll open up in week 14, kind of towards the end of November. And then we have the final. So the final will be comprehensive. It'll be over chapters 1 through 6. Right? And then exam 4 will be over just chapter 5. So Polly's having some audio issues. Killian's is okay. How about the rest of you guys? Can you give me a thumbs up or maybe a thumbs down if your audio isn't working? Thank you, Killian. It's been a good one so far. So I'm assuming it's okay. So maybe Polly. Okay, she's got the captions going good. Those are pretty useful sometimes. All right. So if there's no questions, let's go ahead and get into chapter 5. And so there are some similarities with previous chapters, okay, but there are some differences. And so the main kind of new thing that we're going to learn about in here will be how we go about analyzing relationships between variables. And that's one of the major things we do in science, right? We've got variable A and we have variable B, and we're trying to understand if there's a relationship between them. Okay, and so the techniques we learn in here are quite useful for doing that. Okay, and so the picture we want to have is we have some variable, which we would call the explanatory variable, and we're going to try to understand how it interacts with the response variable. Okay, so there's two variables. The explanatory variable is the one that we suspect may be affecting the response variable. The response variable is the one that's actually changing for some reason, right? And then so there's two of these, and we're trying to understand this piece here where we're seeing how one might be affecting the other. So notice it begins with a hunch or a suspicion. We don't necessarily well, even before we prove that there is a relationship or that one causes the other, we'll still use these words explanatory and response, even before we prove that one causes the other or one changes the other. Okay, so the explanatory and the response, and then we're trying to understand this relationship here. So we'll typically draw an arrow there going from the explanatory over to the response. So broadly speaking, there's two types of associations or two types of relationships between the explanatory and the response variable. We have an association, okay, and an association, it's the weaker of the two types. It just means that as one changes, the other is seen to change as well. It doesn't mean that one causes the other. It just means that they tend to go either in the same direction or in opposite directions. As one changes, the other seems to change. We call that an association, and it's a little bit easier to prove an association. The other kind of relationship that's a little bit stronger of a claim would be causation. And that's where one is actually causing the other to change. Okay, and so causation is harder to prove. but there are ways of doing it, and we'll talk about it here, okay, in this chapter. So some other definitions, we say a pair of variables are related in some way or they're associated. Uh, um, uh, and being associated means they're not independent, okay? And then, so if you have a pair of variables, it can't be both, they can't both be associated and independent, right? And then it's likely you've heard this before. We say that association does not imply causation, or a correlation doesn't imply causation. So just because one's changing and the other's changing at the same time, it doesn't mean that one causes the other. Okay, so let's jump in and look at a couple of examples very quickly here. Okay, so there was a study. It was a very large study that was done. There were over 90,000 women, and they collected all sorts of data and asked all sorts of different questions. But one of the things in there was looking at coffee drinking habits. Okay, and then they were also asking about non-melanoma skin cancer. Okay, so very large study, 94,000, and then so all the participants were talking about their coffee drinking. So, some would drink no coffee, others drank a lot of coffee, and then everyone else was in between somewhere. And then everybody in there had, either had skin cancer or they didn't, this non-melanoma skin cancer. And then, so if you read this study, they concluded that consumption of 6 or more cups of caffeinated coffee was associated with a reduction in the non-melanoma skin cancer. And so they used the word associate or associated. And as we were saying earlier, that's kind of the weaker of the two relationships. So they're not saying that coffee was causing a reduction in the skin cancer. They were just saying it was associated. Um, so what is the response variable and what is the explanatory variable? So there's two variables here. There's coffee drinking, okay, and then there is skin cancer. Okay, so what causes what? Does skin cancer cause? Well, again, we're not necessarily saying causation. I want to be careful there. I'm trying to figure out which one we call the explanatory variable and which one we call the response variable. So we're not actually going to prove that one is causing the other or explaining the other. But if there were some kind of causal relationship, how would it go? Do we think that skin cancer causes a change in or is associated with a change in coffee, or would it be the other direction? I suppose that among people who get skin cancer, that their physicians might recommend that they drink less coffee, right? So perhaps, right, maybe it goes from skin cancer to coffee. That's at least possible, but I think probably the more common sense, intuitive direction would be this direction, right? Coffee somehow explaining the skin cancer, right? Okay, so I'm not saying that it does cause a reduction in skin cancer. I'm just saying that if there were some kind of causal relationship, that's the way it would go. Okay, so in this study, the explanatory variable would be coffee consumption, and the response variable would be non-melanoma skin cancer, right? Or the occurrence, the incidence of skin cancer. Okay. So I mean, this is a very large study, 94,000. So, if this doesn't prove causation, why not, right? If we can detect this relationship, why wouldn't we say that it's causal? Well, it's because of these things called confounding variables. Okay, and it is something we touched on way back in chapter 1. Um, so the picture I like to draw is we've got our coffee drinking, and we have skin cancer. Okay, and if we're not careful, we might say, well, coffee is causing a change in the cancer, okay, incidence rates. But really, what could be happening, we don't know, but what could be happening is we might have something, another variable that's causing both coffee and cancer to change. right? So if we have this third variable, which we would call a confounding variable, it's possible that this variable is actually sort of like the 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 um, the thing that's driving both to change, right? So if we have a third variable that's changing coffee consumption and it's changing skin cancer incidence, then it's possible that it could be this third variable known as a confounding variable, right? So it's confounding because it's confusing the picture, right? And so if we don't include the confounding variable somehow in an experiment, then we can't conclude causation, right? So the picture, it kind of looks like this, right? It looks like maybe coffee's causing a change in cancer, but really it's at least possible that there's another variable out there that's changing coffee and cancer in the same direction. So what are some examples? Well, maybe, you know, it we don't really know what happened, with the people in this study exactly, but we're just throwing out some possibilities. Maybe it's geography, right? So in some regions of the world, they coffee drinking is different, right? So here in the U.S., coffee drinking is very common, but maybe in Australia or maybe in Britain, they might drink less coffee, right? And instead they might drink tea, for example. Yeah. So just take Australia for example. They might be drinking less coffee, and uh, I, I seem to have remember reading that in Australia they have a pretty high rate of skin cancer, right? So maybe they get a lot more sun, right, than in other regions of the world. So there could be some kind of weird geographical confounding variable. Okay, and really you can think of a million of these confounding variables. So I'm just going to name a few. Geography, maybe money, right? So if you're drinking 6 cups of coffee a day, uh, coffee is kind of expensive, right? So maybe, who knows, maybe it's uh, if you're in that group of people drinking 6 cups of coffee a day, you've got more money, right? Perhaps, right? Not everybody, but there might be some kind of statistical average, right? So perhaps it's money. And so if you have more money, you can drink more coffee and perhaps you can get better, uh, health care, right? For your skin cancer, right? So could be money is just changing it, it's changing it's increasing coffee and it's decreasing simultaneously cancer rates, right? So maybe it's money that's that confounding variable in the background, right? It could be a million other things, right? It could be genetics. We just don't know. And that's why the authors of the paper didn't say that coffee causes a reduction in skin cancer. They're just saying it's associated with it. Okay. And so there we go. So can we conclude that drinking 6 or more cups of coffee causes a reduction in the chance of non-melanoma skin cancer? No, we can't determine a causal relationship from an observational study, only a possible association. Okay, so another term from the past. We talked way back in chapter 1 about the 2 types of studies that we do in statistics. So broadly speaking, there are observational studies and there are experiments. Observational studies are where we just sort of passively observe what's going on. And that's what they were doing here, right? They were just asking questions about their coffee drinking habits and their skin cancer, status, right? So this was an observational study, and typically with observational studies, we cannot prove a causal relationship, okay? Only a possible association. So of course, we would love to understand causal relationships, but still, if you can show that there's an association, that's a step in the right direction, right? That's still useful information, and that might lead to an experiment in the future, right? So we love observational studies, and we love knowing about possible associations. It's very very useful, even though we would if we can like to take it to the next step and understand causality as well. Okay, so does that make sense? So you'll see this on the fourth exam, and on the final, we'll have some scenarios with a study, and you'll get this question. It'll say, can we determine causality and or that one causes another, something like that. If it is an observational study, then no, you cannot determine causality. Okay, so the only way we can determine causality is with an experiment, which we'll see in just a little bit. Okay, so I want you guys to try some of these. We don't have time for probably everyone to do every one, so I'll just kind of assign a few here. So Brock, if you could do number 1, Delmy, if you could do number 2, Devin, number 3, Haley, if you could do number 1, Julie, if you could do number 2, Killian, if you could do number 3, Lana, number 1, and Laura, number 2. Okay, or if you don't like the one I assigned you, then just choose one of the others. Just kind of read through it, see if you can identify the response variable, see if you can identify the explanatory variable, and yeah, be in a good spot here. I'll go quiet for a couple minutes and get more comments. Anybody get it? So for number 1 here, so I'll read through it. So we have researchers, they've collected data and they're looking at the relationship between pollutants and preterm births, right? So I think preterm means the baby is about at least a month or more early, right? And so typically, it's not something we want to see too much. I think it is associated with some problems later on. So they're trying to see if the pollutants are causing this preterm birth issue. So let's see. So Brock and Devin have some here. So the response is, oh, okay, let's see. Devin's doing a different one. Okay, so Brock, preterm explanatory pollutants. Yep, good. Yep. So there's 2 variables. There are the births, the preterm births. Okay, so we'll just call it preterm for one variable. Okay, so every birth is either going to be preterm or not. And then there is some level of pollutants, right? And so, we're this study doesn't necessarily prove that one causes the other. So when we say explanatory, we just mean the one we would suspect would be causing the other, right? So do preterm births cause pollutants? Probably not. You'd have to engage in some, kind of mental gymnastics to make that the case. Um, it's just hard to people would laugh at you, right? If you said, well, the preterm births are causing the pollution. So, it's most likely the pollutants would be causing, preterm births, right? So, great. So that's what looks like most of you are getting here. So yeah, we would say whether the baby was born prematurely, okay? And so that would be a yes or a no. And then the explanatory variable would be, I think I've got something going on here with this. I think that's supposed to be for the next one. Hold on 1 second. Let me get rid of this. I'm not sure what happened there. Let me type this in here. Yeah, so the explanatory variable would be pollutants, right? So, okay. Or air pollution exposure, we could say. So they would have some way of measuring the air pollution for the the pregnancies at that time, right? Good. So there's the explanatory variable. Okay. Then in number 2, good. So we've got a study looking at the effect of antibiotic treatment for acute sinusitis. Participants were either given a 10-day course of amoxicillin or a placebo. At the end of the 10 days, they were asked whether they had experienced improvement in their symptoms, right? So there's 2 variables. There is the treatment that you get, right? So you're either going to get the medicine or the placebo, right? So that's one variable, and the other variable is improvement in symptoms, right? So it's pretty obvious that the explanatory would be, as you guys are saying over here, what treatment they got, right? So did they get amoxicillin or not, right? And then the response would be, did their symptoms improve? Yes or no, right? Good. Then on the third one, this is this is a topic you'll see economists and education researchers talk about a lot. The relationship between per capita income and education. It's one of the big arguments for education, right? Is it's good for the economy, right? So, uh, so they're looking at 3,000 counties in the U.S. and for each county they record. Oh, let's see here. Lana is saying. Let me get to that one later, Lana. That's a little bit uh, different kind of it's a little bit in a different chapter. So email me about that one if you would, Lana. Um, no worries. So we've got 3,000 counties, and they recorded the percent of residents who had a bachelor's degree and the per capita income in each county, right? And so there's 2 variables. There's bachelor's degree percentage, and then there's per capita income. And then they're trying to see if a higher proportion of residents with bachelor's degrees led to higher per capita incomes. So there's 2 variables, right? There's you could call it like education level and then the income level. And so you could make the argument in both directions, I think, pretty easily. Um, I think the more obvious here would be to say that education is causing income, right? So the per capita percent of residents with bachelor's degrees, and then that would be causing some change in the per capita income or explaining the per capita income. Good. And that seems to be what most of you guys are saying over here in the response over in the chat. So great. You could probably make the other argument. Let's say you live in a very wealthy location. Um, so if you live in a very wealthy society, then there's more money for education, right? So it might be easier to go to college. So, it might work the other way too. But yeah, I think definitely the most common sense here would be to say that bachelor's degrees percentages is causing or explaining the per capita income level. Good. So there we go. So it's kind of a discussion there of some ideas about relationships between variables. It's a major topic within stats and just science more generally. So that's mostly association, and that's great. I mean, so much important stuff is just talking about association. Very interesting to detect and explain and establish new associations. But we would like to go beyond that if we can and talk about causation. So with causation, we are actually making a claim that one variable causes another to change. And you can probably imagine that this is harder to prove, right? There's a higher bar for this because you basically have to filter out those confounding variables. Okay, um, so how do we do it? Well, there is a device for doing that. Okay, that device is called the experiment or an experiment, and the best kind of experiment is a randomized experiment. Okay, so what's an experiment? It's a type of study used to investigate the possibility of a causal connection between the explanatory and response variables. And the way you do this is you focus in on one variable that you're trying to understand, and you change that one variable. Okay, so you have your explanatory variable here. You have your response variable. Okay, and the idea is you're going to alter the explanatory variable in some way. You're going to turn it off, you're going to turn it on. You're going to dial it up, you're going to dial it down somehow. You give them a new treatment, or you give them a placebo, something like that, right? So you change the explanatory variable and you observe what happens with the response variable. Okay, so you actively alter the explanatory variable. You make people exercise, you give them a vitamin, something like that. And then you watch to see what happens with the response variable. Okay, so if you're actively altering the explanatory variable, then you're doing an experiment. Okay, now some experiments are better than others, and we want to talk about the principles of good experiments. So the first principle, just like with many other studies that we've encountered, would be randomization. Okay, so when you're altering the explanatory variable, you'll typically have two or more groups. You'll have a group that forms a baseline, and you might also give them a placebo. So you're not changing anything with them. They're just sort of getting the standard treatment or no treatment at all. And then you have another group that's getting the new treatment, right? And so one of the most important principles is that we randomly assign individuals to one of those two or more groups. Okay, so the experiment, we do want to have this randomization. So that happens when the individuals are randomly assigned to either get some treatment or to not get a treatment. Okay. So, so as we were saying earlier, association does not equal causation. So in data analysis, which would be more kind of an observational thing, association does not imply causation, but causation can be inferred from a randomized experiment. Okay, so as I was saying, not all experiments are as good as other experiments. Some are better, and so part of the point of an experiment is to be able to filter out those confounding variables. So how do we do that? Well, there are 4 principles of experimental design that we talk about in here. Okay, the first one is controlling. The second is randomization. The third is replication. The fourth is blocking. Okay, so let me just define those quickly, and then we'll have some examples of each. So controlling is where you assign the treatments to the observational units, and then you try to make every other difference as minimal as possible, right? So if you want to understand how some new cholesterol controlling medication works, then you really want to, you get your 2 groups, right? You get your treatment group, you get your control group, and you want those 2 groups to be as similar as possible in every way except for the treatment, right? And what that does is it filters out other possible confounding variables, right? It filters out income levels, geography, genetics. By making those 2 groups as similar as possible in every way except for the treatment, then you can filter out, or you can have a better chance of filtering out those confounding variables, right? So that principle is called controlling. Okay, so you control the other differences as much as you can, right? So that's the first principle. So we like controlling, right? Second principle is randomization. So we already discussed that. So we're typically going to have at least 2 treatment groups. Okay, and then so depending on what kind of medicine or what kind of treatment you're designing, right? It could have multiple levels. So you could have 2 groups, you can have 3 or 4 or even more groups, but you do need to have at least 2. Okay, and then you randomly assign people to those various treatments. The third principle is replication, and it's easy to get confused by this word. Some people, some students assume when we say replication, it means that you redo this study and you prove, that you get the same kind of results. That is replication, but it's a different use of the same word. When we say replication in experimental design, we simply mean that you have a large enough sample. Okay, so how large is large? Well, as you've seen, there are formulas for calculating sample size. So we have ways of determining how large of a sample we need, but replication simply means you have multiple people in the study, multiple people in the experiment. Okay, so you're not just experimenting on one or two or three people. You're experimenting on enough people to get um, inference, right? Okay, and then fourth is blocking. Okay, so now blocking is it's basically a type of controlling. There's certain differences that are kind of difficult to control for. So what we'll do is we'll block people based on those differences. Um, and we'll see an example of that as well. Okay, so, and then just a few more terms down here. The treatment group is the group that receives the drug or the treatment that's being tested. It's not always drugs, although the pharmaceutical industry is a major, it's one of the industries that uses statistics the most. Okay, so it often is drugs, but it could be other things as well. Then the control group is the group that did not receive any treatment. Okay, so why do we have a control group? Well, the control group is there to help us establish a baseline, right? So if you're treating people for a disease, well, it's possible, so if you're treating people for a disease, right, you have this new treatment, and so you give them all the medication, and let's say a lot of them get better, right, after they receive the medication. It's possible that they got better because of the medication, but it's also possible they just got better because, sometimes you just get better after you get sick, right? So with the control group, what you can do is establish a kind of baseline level of people who would just kind of get better naturally, right? Just kind of, with their own, natural immune system processes, right? So with the control group, you can actually compare the treatment to, basically get an idea of how much better the treatment is than not getting any drug at all. Okay. Then a couple of other important principles. We have the idea of blindness. Okay, so we say that an experiment is blind when the researchers do not tell the patients which treatment they're receiving. Okay, so this is an important thing because of this thing called the placebo effect. Okay, so this is something that's quite fascinating to me, and as I understand it, this has been pretty much, I mean, this has been established to be the case that some people, not everyone, and not for every illness, but for certain illnesses and certain people, some people will get better just because they think they're getting a medication that works. Okay, yeah, great. I agree with you, Alana. It's really fascinating, and so they prove this that this is the case. Again, not everybody and not every illness, but there are some people that will, if you give them a fake medication, they will actually get better. Okay, so why does this matter? Well, it could be that people in the treatment are getting better not because of the medication working, but just because they think they should get better, and they actually do get better. And so that's part of what the control group will do for us. Okay, so the idea is if we can give the control group a placebo, right, which is a fake treatment, like an inert pill or like a sugar pill, or like an injection that's really just like some kind of saline solution or something, then you can also filter out the placebo effect. Okay, so that's what the control group will do for us. It'll help us filter out the placebo effect, and it also establishes a baseline for just sort of like what would happen if they didn't receive the medication at all. Okay, and then so blindness is important because again, because of the placebo effect, you don't want people to know if they're getting an actual treatment or just a fake treatment, right? And then finally, this is it's kind of depressing in a way, but it is true that researchers, just like other people, they have interests, right? Their own self-interests, and so if researchers know what medication or what treatment their subjects are getting, they can actually kind of read into the results, and they can sort of even maybe not consciously, it might be subconsciously, they can actually affect the results of their study. So with double blind, that's where the researchers, the doctors who interact with the patients are, just like the patients themselves, unaware of who is receiving the treatment. So we like to have blindness. It's a good thing when it comes to these experiments. And if we can have a double-blind experiment, that's great. Okay, so these are all things we want to have in our experiment. So let's do one. Or let's look at an example here. So we have mental health and exercise. Okay, so two variables, exercise and mental health. And so, maybe mental health does affect exercise levels. If you're in a bad mood, probably it's a little bit harder to go exercise. So, we could say mental health, explains exercise, but I think it's more typical that we would think of exercise as uh, explaining mental health in some way, right? So the explanatory variable here is exercise, and the response is mental health, right? So, so this researcher proposes the following study. We get a stratified random sample of various people from the population. Okay, so we've done this by age group, and then we're going to randomly assign half the subjects from each age group to exercise twice a week and instruct the rest not to exercise. And then before you get going with this exercise program, you conduct a mental health exam. Okay, and then also at the very end, you conduct another mental health exam. Right, so for everybody, there are two mental health exam scores, or um, surveys that are done, and so you can get an idea of the difference in their mental health level. Did it improve? Did it go down? Is it the same as before you started the exercise program? Okay. Now, why did they use these age groups? Well, it's because they suspected that maybe younger people and older people would have a different relationship between exercise and mental health. I think it's at least possible, right? So if you take younger people, um, maybe the way exercise affects their mental health is different than for the way older folks, 41 to 55, maybe it's different for that older group, right? So maybe when they exercise, it has a slightly different effect on their mental health, right? And so what they've created here are blocks, basically. So they're thinking, well, maybe age might be one of these confounding variables, right? So they're going to use blocks to control. Okay, so is this an observational study or an experiment? Well, pretty clearly this is an observational study. I'm sorry, an experiment, right? Because they're changing the explanatory variable for these people, right? So again, we have exercise and we have mental health. And so we would suspect the arrow would go like that. And what they're doing is they are causing a change in the exercise, right? So of course these were people who are willing to do this. It's not like they're being forced and to do this. So they get contacted and they say they'll participate, and then they're willing to either exercise or not exercise. Okay, so we're changing the exercising variable, and then they're going to observe what happens with that what happens with that mental health variable. Okay, so it's an experiment. So are the four principles of experimental design incorporated in the study? Let's draw this out. So you guys remember the stratified random sample. With strata, we have these non-overlapping groups. And in this case, it's non-overlapping by age, right? So we have the younger folks, 18 to 30. We have this middle group here of people in their 30s, and then these kind of more middle-aged people over here. Don't really have any seniors in here, but so we could make the blocks even smaller. Maybe you think, well, 18-year-olds and 30-year-olds, they're different, and it's possible, but at least it is kind of blocking by age a little bit here, right? So these are blocks, and then within each block, we give some the treatment and some the control, right? So the control would be to not exercise, right? Right. So the rest are not instructed to not exercise. So the control here would be like not exercising. Okay. And then the treatment would be to exercise. Then within the 30-year-old group, same thing. Some are randomly assigned to exercise, and then some are randomly assigned to not exercise. Okay. And then with our third group here, some are instructed to not exercise, and then others are instructed to exercise. Okay, so we have people in each one. Okay, so within each block there, we're basically filtering out age because we're treating pretty much everybody from 18 to 30 as young and kind of having the same effect, right? And then the same for the other age groups. So what this allows us to do is filter out age as a confounding variable. Okay. So are the four principles of experimental design incorporated in the study? Yes, right? We have controlling. So what they're trying to do is make people, so they have their sample, and then they want to, make these groups as similar as they can, except for the treatment, right? And so the example here is with age, right? They're trying to control their accounting for age. And if they have a large enough sample, they can make these even smaller blocks, right? They could do 18 to 25 and 26 to 30, etc. Okay, so they are using controlling here, right? And then so they are doing randomization. It says that they are randomly assigned to either get the treatment, which is exercising, or to not get the treatment, which would be considered the control. Okay, so they're randomly assigned into treatment and control. Replication, again, replication doesn't, in this context, we're not talking about redoing the study to verify results. What we're talking about with replication is having a large enough sample, right? So again, we don't want to do this on just like two people or one person, right? And I know that sounds obvious, but you hear people talk about that all the time. They'll say, well, this worked for my buddy, right? Or, this didn't work for, my cousin or something like that. And they try to use that as an argument, right? For a causal relationship, right? But that's not really going to cut it, right? For a formal experiment. So replication just means we have enough people in the treatment and enough people in the control. So it's not really clear here how many people were included, but they did say representative proportions. So they must have had, several, at least, several people in each of these groups. And then blocking, they did do blocks, right? They split people into age groups first. Okay, so they were trying to control for that age difference as much as possible. Okay, so if there are statistically significant results, can we conclude that exercising causes improved mental health? Okay, so what that means is they would do some kind of test, right? A hypothesis test. They would get a p-value, and then let's say the p-value is lower than alpha. They reject the null, and are they justified in saying that exercising causes improved mental health. Okay, so, you know, it's good to be skeptical, and we don't want to just go around believing anything we read about. But at the same time, it is good to be able to make progress, right? It's good to know like that something causes something else, right? So if we have an experiment, a randomized experiment, and we have principles of experimental design in place, then at the end of the experiment, if you believe in the scientific process, then the answer should be yes, right? I mean, if you believe in how experimentation works, and we have a well-designed experiment, and we do have statistically significant results, then the answer really should be yes, right? If you say no at this point, then I don't know what to tell you. Like, how else are you ever going to, be convinced of anything, right? So if so on, and and on the exam, right? If we give you one of these experiments and you can tell that it's an experiment, and it they used the principles of design, experimental design. If the results are statistically significant, then the answer is yes. Okay, so on the exam 4 and on the final, you'll be given one of these scenarios, and if it's an experiment that was run correctly and properly, then at the end, if we ask you, can we conclude that one causes the other? The answer is yes. Okay. Now, if it's an observational study, then you say no because there's confounding variables, right? So, all right. So you guys try some of these. Okay. So, um, okay. So let's see here. Brock, Delmy, and Devin, you guys do number 1. Haley, Julia, and Killian, you guys do number 2. Lana, Laura, and Noah, you guys do number 3. Fabrita, Polly, you guys do number 4. So read the scenario and then determine if it's an observational study or an experiment. Okay, and then whether causation can be concluded. Okay, so on number 1, we have rats with cancer. They're divided into 2 groups. One group received 5 milligrams of medication. The other received 10 milligrams. After 2 years, the spread of cancer is measured. Okay. So what do you guys think? Is this an experiment or an observational study? And then yes or no, can we conclude causation? Great. So Haley is saying this is an experiment. Yep, great. So let's see. They're altering, right, how much medication they receive. Okay, so it's an experiment. And the only thing here is it's not really saying how they're divided into groups there. Okay, so it just explains the experiment in like 3 sentences. So it obviously isn't giving us all the information here, like how many rats were there. But yeah, I would tend to think, yeah, we can conclude causation. Maybe the only thing I would worry about is randomization. But again, it's not giving us a ton of information here about this study. So if there was randomization and the other principles of experimental design, then yes. Okay, so you can say yes, causation can be concluded here if there was randomization. Okay. All right, so then we have conservation agents netted 250 largemouth bass in a lake. They measured their length and determined how many were carrying parasites. Okay, so let's see who did this one. I'm not seeing anything from anybody on number 2. Was this an experiment or an observational study? Well, let's see. Are they? Yeah, it's observational, right? They didn't like introduce parasites into the lake or something like that. At least that's not what it sounds like. And so there's 2 variables. There's the length of the fish, and then there's parasites, right? The presence of parasites. So this would be, parasites causing length, right? Or the explanatory variable would be parasites. The response would be length. But they're not, again, they're not like introducing parasites into the fish. So this would be observational. So we cannot conclude causation. Okay, good. 7th grade students are randomly divided into 2 groups. One group is taught math using traditional techniques. The other is taught math using a reform method. After 1 year, each group is given an achievement test to compare proficiency. Okay, so we do this a lot in education. We'll have these new techniques, and then we try them out and we see if it works, right? So let's see, what do you guys think here? Experiment. Yep, Lana, you're right. This is an experiment, and they are randomly divided, right? So this is a randomized experiment. Okay, so assuming that the rest of the experiment was done correctly, then we can conclude causation. Okay. If you can't conclude causation from a randomized experiment, how are you going to ever be able to conclude causation, right? Do another experiment. Well, why would the other experiment be better than this one, right? So if it's a properly run randomized experiment, then yes, we can conclude causation. Okay. So a survey was conducted asking 400 people their gender and do you prefer Coke or Pepsi? Did anybody get this one? So probably the explanatory variable would be gender, and then response would be soft drink preference. So yeah, Polly's got that one. It's observational. The people running the study weren't, they're not changing the explanatory variable in their subjects, right? So it's observational. And then again, since it's observational, we cannot conclude causation. Okay, great. Any questions there? I don't think it's the understanding that the basic idea is probably not too bad. Now, actually carrying out a successful experiment or even an observational study can be quite complicated and quite difficult, but I think understanding the basic principles, usually that goes pretty well for students. Any questions there about that? Okay, well, moving along, making good progress here. So, stats has a lot of, vocabulary in it and a lot of principles and concepts. And then it also has lots of math, right? So we're going to get into the more kind of quantitative side of it, and we're going to learn techniques for helping us take the results of some observational study or a randomized experiment and actually start to think about, how can we actually show that the difference between a treatment and control is actually um, statistically significant, right? So here we're going to introduce our quantitative tools for analyzing relationships. Okay, so 5.1 and 5.2 are kind of the principles that we use in our observational studies and our experiments. But then once we get our data, we need to have actual quantitative tools for analyzing these relationships between the variables. Okay, so again, you've got the new method for teaching math, you have the old method for teaching math, and you run an experiment, you get results. So how do you actually prove that one group did statistically significantly better than another group? Okay, so that's what 5.3 is going to help us with. We're going to learn these tools for looking at the results of an observational study or an experiment and trying to kind of quantify the strength of the relationship. Okay, so there's 4 of these that we're going to talk about. If you take more stats in the future, you'll learn lots of others as well. This is a very, very difficult, it can be a very, very difficult thing to do. So we begin with what's called the contingency table. Okay, then we'll have the marginal distribution. Then we have what's called the conditional distribution. And then finally, we'll have a new graphic here. It's called the segmented bar graph. Bar graph, bar plot, bar chart. Okay, so all right, so one of the main things of chapter 5 is we're thinking about experimental design and the principles of experimental design. The other major feature of this chapter is the type of data we're going to look at. We're going to be looking at 2 categorical variables. Okay, so it goes well with experimental design, right? Because you might look at a new drug, right? Did they get the treatment or the control? Well, that's categorical, right? You either got the treatment or the control, so it's a yes or no. And then either you got better or you didn't, right? So that's also categorical. So in chapter 5, the type of data we're typically going to be looking at is a categorical variable and another categorical variable. Okay, so this 2 categorical variables relationship, it's right at the heart of quite a lot of studies that are done. Okay, so these are the beginning. This is the beginning here of the quantitative tools for analyzing those kinds of variables. So what is the contingency table? Well, it's a table, and it's used to summarize data collected to analyze the relationship between 2 categorical variables. So it's probably just easiest if we look at one. So in this example, there was a survey. Okay, so automatically we know it's probably observational, but that's fine. Still is useful to observe. And we're looking at happiness and health. Okay, so two important things for all of us, right? The level of health we enjoy, and then the level of happiness we have, right? And so psychologists would have, and they do, they've got all sorts of different tests that they've developed and techniques they've developed to understand people's happiness levels. So we'll take a rather simplistic one here where there's 3 levels. You're either not too happy, you're pretty happy, or you're very happy, right? And so so we'll say everybody is at one of those 3 levels. And then when it comes to health, same thing. There's various tests that health researchers have developed, right, that can help classify people as far as how good their health is. So we'll go with, again, a pretty simplistic one. Either you're in poor health or you're in good health. Yeah, pretty happy versus very happy. Yeah, I mean, some fields, you know, those variables can be a little bit more subjective, right? A little bit more open to interpretation. And some people really like that. Some people, other people don't like that, right? So, different kinds of research appeal or not to various people. So yeah, poor health and good health, right? So you're either in poor health or you're in good health, right? And you're either not too happy, you're either pretty happy or very happy. And so the way we've defined it here is that we have a categorical variable. Okay, so your health status is categorical here. Okay, you're either in poor or in good health, right? So it's a yes or a no. It's a category. And then if we define happiness, or if we have this happiness variable with the three levels, that's also categorical. Okay, so your happiness level is also a categorical variable. So the idea is, does happiness, do happiness and health, are they connected in some way? And what would be the explanatory variable anyway here? Does health cause happiness or does happiness cause health? Well, probably being in a good mood can improve your health, but I think for most of us, the most kind of common sense answer would be that health would be explaining your happiness. Okay, so that's the kind of thing we're thinking about here. And again, there's two categorical variables in the way they've set it up here. So we have a row variable and a column variable. So the happiness is the row variable. The health is the column variable. So every contingency table will have a row variable and a column variable. Okay, let's see here. Yeah, good. Health is wealth. Yeah, I mean, it's so true. Like, I, when I'm healthy, I don't really think too much about it. But as soon as I get sick, yeah, that's all I can think about is, gosh, I wish I were healthy again. So yeah, definitely, if you just ask me, does health change your happiness? I would say yes, right? But who knows? Maybe it doesn't. Maybe there, or maybe it does, but it's a weak kind of relationship, right? Who knows? So that's what this table will help us with. It'll help us get going with some quantitative measures here. So how do we work through this? Well, so this is the contingency table. Okay, and so what does it tell us? Well, I think, it's a little bit hard to look at it and get much of a read on it. You can kind of maybe make some observations. So if we look at the people in good health, it does appear that we have quite a lot of people that are either pretty or very happy, and not a whole lot of people who are not too happy. In the poor health, they don't seem to have a lot of very happy people, but it doesn't look like it's equally split between poor and good health, right? So maybe it's just kind of hard to see because of the varying frequencies in the two health categories, right? So we want to go beyond just staring at a contingency table, and that's where the marginal distributions come in. Okay, so with the marginal distribution, we're simply going to add um, the number in each row and then add the number in each column. Okay, so that's called the marginal distribution. Okay, so it's in the margin, it's on the edge of the table. So we add up and put it in the margin, right? So 43 plus 30 is 73. 61 plus 189 is 250, right? And then if we go vertically, 43 plus 61 plus 22 is 126. Okay, so you guys do the other two. Do this one, just make sure you understand this. There's nothing, super theoretical or abstract here about this. We're doing addition, okay? So just add across for the very happy and then add down for the good health. And we have what's called the marginal distribution. So does anybody have it? What would be here for the marginal distribution for very happy, or what would be the frequency there? Great, thank you, Noah. having 144, and then if we add vertically here, 341. Okay, so it's just addition, but it's smart addition. We're adding in a table that's organized in a way that I think will help us understand this relationship first. Understand this relationship well. So I forgot to mention what each of these numbers mean. So up here, the 122, that means there were 122 people who were both very happy and in good health, right? The 61 here mean that there were 61 people that were in poor health and who were pretty happy, right? So you take everyone in your data set and everybody's going to be in one of these 6 cells of the table, right? So then by adding horizontally and vertically, what do? Well, this is what I call a univariate analysis. We're not really understanding the relationship yet between the two variables yet. What we're trying to do is just understand the individual variables by themselves. So what does this mean? It means that most people, the most common level is pretty happy. And that's good. I mean, it would be nice if everyone, I guess, were very happy, but at least, uh, you know, pretty happy is the most common category. So that's good. And then between not too happy and very happy, well, the very happy, there's twice as many in the very happy than in the not too happy. So that's great news, right? I mean, it seems like most people have some kind of happiness level, some kind of satisfaction, right? Um, and then this category of not too happy is fairly, it's not I wouldn't call it rare, but it's the least common of the three. So that's good news. And then what do the totals down here tell us? Well, again, this is I call it univariate. So when I say univariate, I mean one variable. And so what the two numbers down there tell us, they tell us how health is distributed, right? So not health and happiness, but just health itself. And this also is kind of is also seems to be good news to me, right? So the good health is a little bit more than twice as common as poor health. Okay, so obviously there still are a lot of people in poor health, but the number in good health is a lot higher than in poor health. Okay, so that's by constructing the marginal distribution, you understand the individual variables by themselves, which is important in your study. What happens if you add up all of the numbers in the rightmost column? You get 467. What happens if you add up the numbers at the bottom? You get the same thing. And what that tells you is the size of your data set, right? Which could be typically is a sample, but it could be a population as well, right? So we have 467 people in the study. Okay. So that's our marginal distribution. So 2 down, 2 to go. What comes next? The third is where well, actually, we still need to talk about the relative frequency. Okay, so we're still on the marginal distribution. There's 2 marginal distributions. There's the frequency, and then there's the relative frequency. And you'll remember this from when we were doing bar graphs, right? Bar charts, bar plots. 73 sounds like a lot, but it's not that much if there's like 10 million in the study, right? 250 might not sound like a lot, but if there's 300 people in the study, then that's a lot, right? So when we talk about the relative frequency, we're talking about relative to the total number in the study. Okay, so we're going to take each of the numbers here and simply divide by the 467. So the 73 over 467 gives us 0.156. So about 16% of the people in this study were not too happy. Do you see how that gives us more, it gives us additional information? It's quite useful to know that there were 73 people who are not too happy. But in a way, knowing that 16%, that's even in some ways more useful, right? Because then I can sort of extrapolate and get an idea of kind of in general, like, what is the happiness level among people, right? So Yeah, it sounds pretty good to me, right? Only less than a fifth of people are not too happy. Okay, and then if we went down to say here, that would be 126 divided by 467, which is 0.27. So about 27% of people are in poor health. Okay, so maybe that's more than it should be, but at least it's not, majority. Most people do seem to be in good health. So I want you to calculate these other relative frequencies. Just make sure we're all on the same page here with this. And it's not the most complex thing we've done all semester, right? All we have to do is add vertically, horizontally, and then we do a simple division, right? So we're just at the level of arithmetic, but even with the humble arithmetic, we're able to do some important descriptive statistics here. Okay, a lot of important stuff comes about by doing addition and division in a contingency table. Okay, so all right, can anybody give me one of these? Let's say what percentage of people are pretty happy, or what proportion of people are pretty happy? 0.535, exactly. Good. Thank you, Noah. Any questions about how we're getting these numbers? Okay, where did that one come from? Well, we took the 250 over here, we divided by 467, and that gave us the 0.535. Okay, so you just run down your column here and across the row at the bottom, you divide by the sample size or the population size. I'll write the rest of these in, and then just let me know if you have any questions about any of those. Okay. Great. Thank you, Julia. That's exactly right. 0.308. Awesome. Thank you. Okay. Any other questions there? Okay. Well, perfect. Let's keep going. So that's the marginal distribution. And again, it doesn't tell us much about the relationship between the variables, but it does help us understand the variables, by themselves, right? Which is important. So the next step is to start investigating the relationship between the variables, right? I mean, that's kind of the point of the table. So we're going to move now to the conditional distribution. So it's the same contingency table, but now when we do the division, we're going to divide not by the total number, but by the number in that category. Okay, and we'll see that this will actually allow us to see what happens to happiness when we switch from one level of health to another. Okay, so so this is the conditional distribution. So when you say conditional, then you have a condition, right? You have, something that's changed. And so here we're going to condition on level of health. That's the explanatory variable is health. So we're going to condition on the level of the health, right? So the first thing we'll do is we'll look at the group of people that have poor health. Okay, so there were 126 of those. And then so among those 126, 43 were not too happy. So I'm going to take the 43 and I'm going to divide by 126. Okay, so earlier we divided by the 340, I'm sorry, how many was it? It was the 467, right? The total number in the study. But now we're only going to divide by the total number of the group that we're conditioning on, which is the column variable, right? So there are 126 in there, which was 0.341. So about 34% of people in poor health are not too happy. Okay, so the numerator will be whatever. So the numerator for that cell will be the value it was in the contingency table, but the denominator will be changing depending on what column you're in. For example, if we look at the people in good health who are not too happy, we have 30, but this is out of people in good health. So we have 341 for the denominator there. So what is that? That's about 9%. So 0.088. Okay. So let me do one more and then I'll have you guys try the rest of them. Okay, so let's see. So for pretty happy, if we're looking at people in poor health, there are 126 people in poor health and 61 of them are pretty happy. Okay, so if we go 61 divided by 126, it's going to be 0.484. So among people who are in poor health, most of the people, well, not most, but it's pretty close to 50% are pretty happy. Okay, and then so if we move over to good health, so among the people in good health, there are 341 of those, 189 of the good health folks are saying they're pretty happy, which is 0.554. So among the folks with the good health status, a majority of them are pretty happy, which sounds pretty good to me. Okay, so you guys try the last two there. Find the conditional there for very happy, for the poor, and the good health for the very happy. Okay, let's give that a try, and then we'll be pretty much done with our conditional distribution. And I think you'll be able to see pretty quickly why this conditioning on the explanatory variable can give insight into the relationship between the variables. Great. Thank you, Julia. That's exactly right. Good. So we have 22 over 126, which is I got 0.175. Let me see here. So if we go okay, it's 175. Okay, good. And then on the other one, great, 0.358. Okay. By the way, if you add up all of the totals by column, you should get approximately 1. Why not exactly 1? Well, if you're not rounding at all, then you do get 1. But often, especially when you're doing this by hand, you'll have some rounding, and then by the time you round, it can introduce some slight deviations from 1. But so if you get 0.997, it's probably fine. If you get 0.58, then you've made a mistake, right? So it's good to just double check these things. It's so easy to miss a number here or there. So by adding down the columns, you can just cut down on errors. Okay. All right. So let's answer a couple questions. What proportion of people in poor health are very happy? There still are pretty good number of people in poor health who are very happy, but it's much smaller than the proportion of people in good health who are very happy, right? If we look over here, the people in good health, almost 40% of them are very happy. Okay, and we see a similar thing for all of the levels, right? For among the not too happy, it goes way down when you go from poor health to good health. It drops from 34% down to 9%. And then in the pretty happy category, which is still a good place to be in, it does go up there, right? So we see the same thing for all the levels of happiness. It's going to, it's going to go in the improved, direction when we go from poor health to good health. Okay, so was this an observational study or an experiment? Well, this would be an example of a time where it's really hard to do an experiment because what would you have to do? You would have to change somebody's health status, right? So, obviously they can't like take a healthy person and make them sick, right? And then see what happens to their health. So, isn't it, it's an example of how, experiments are somewhat limited because of, ethical considerations. And so this would definitely be an observational study. So we can't conclude that health is causing happiness to change. We can get quite an a strong suspicion that that's the case here. but we can probably conclude some kind of association, right? Okay, so yeah, it does seem that good health, that health is associated with happiness. There is a fourth technique that we have, fourth quantitative analytical tool, and that's a graphic this time. It's the segmented bar plot. Okay, so the segmented bar plot is basically a graphical depiction of the conditional distribution. Okay, so with the segmented bar plot, it's a bar plot. Remember, bar plots came from our chapter on categorical data. So I think this is chapter 2. What we're going to do is we're going to take the explanatory variable and we're going to plot, we're going to have a column for each level of the explanatory variable. And then, so that's the bar chart part of it. And then we're going to segment each of the bars, in this case, each of the 2 bars by level of the response variable. So we're going to have a bar above the poor health. We're going to have a bar above the good health. And then each one gets a bar. The bars are the same height, okay? At least when we do a relative frequency, which is what we typically will do, because each one has 100% of the people in that level of health, right? So each bar goes to 100% or to 1, and then within each one, we're going to segment on the level of the response variable. So it probably is useful to watch it constructed step by step. Okay, it's good to see kind of the final product there, but let's kind of demonstrate how to put it together. Okay, so we would have the poor health, we have the good health, okay, and then so we'll have a bar for both, and then that bar is going to go up to 100%. So because we have to account for everybody in the poor health, we have to account for everybody in the good health, right? Oh, darn it. Wow, I just went over big time, didn't I? I was wondering, where is everybody going? Wow, I went way over. Sorry about that. Feel free to, feel free to let me know in the chat if I go over. That doesn't happen to me. But let me stop there. We're well over time. So yeah, we'll stop there. We'll come back and we'll talk more about this bar chart here on Tuesday, right? Yeah. So yeah, good. Any questions about anything before we break here? So next Tuesday we're just gonna keep going here through chapter 5. And yeah, so have a good one. Happy Halloween, everybody. And see you back here on Tuesday. Thanks, everyone. Bye.